So I am from Oklahoma State University. I'm a PhD student there, and my supervisor is Professor Dr. Dev Mishra. So today I will talk about discrete or point-based measurement system, rail-tie interface using strain gauges. So before I go to the presentation, I'd like to acknowledge all of my co-authors, my professor, Dr. Dev Mishra, and Radim Brujek and Rakan Altur from ENSCO, and Dr. Ted Sussman from US Volpe Center, and Hugo Thompson from Federal Railroad Administration. So generally every in a railroad track, the wheel load is distributed in between 5 to 7 tie. And the maximum percentage of load carried by a specific tie is generally in between 35 to 50%. And these percentages can vary for several reasons, such as tie spacing, tie stiffness, and rail pad stiffness. Overall, the subgrade stiffness can vary these percentages. So tracking, but one of the most important things that when the support condition changes, this variation can be noticeable. So identification of this pattern or what is the rail tie interface reaction force can tell us what is the subgrade condition in the track. So generally, this rail tie interface reaction force is measured by load cell, and there are some other technologies such as the instrumented type data they use. But another thing is a strain gauge that can be also used to measure the rail tie interface reaction force. And this theory was proposed by Dr. Adbach et al. In 1979. And in his theory, he used a strain gauge to measure the differential shear strain in two locations. One is called in between two ties, as shown in the figure. And in another case, he installed the strain gauge over a tie. So the instrumentation setup over a tie is called tie circuit, and another one is called Priest circuit. So from Priest circuit, they measured, generally it's measured the wheel load or applied load. And in tie circuit, it's measured the resultant of applied load and also the reaction force that is experienced in between a rail and tie interface. So when we subtract those two things, we will get the rail tie interface reaction force. So here is the equation in the bottom showing that the yellow portion is from the differential shear strain part, and this differential shear strain is related to the load, applied load through geometric property of the rail. So installation of a strain gauge in the field and the geometric property that is already a rail of the field is sometimes very difficult to get. So generally, to bypass the system, we use a kind of calibration system in the field. So once we install the strain gauge, we calibrate and bypass the necessary requirements such as geometric properties. So industry people and several researchers use different types of calibration frame. In the right side, it shows a triangular loading frame, which is called A frame, sometimes called it is delta frame. And in another system where the left side of the picture, where the empty car weight used as a frame to push the rail in a specific location so that the strain gauge circuit can be calibrated. So the question, several cases it was one of the question that so we are using different types of A-frame and different types of configuration to calibrate the strain gauge, will it work in the field when there is a dynamic load will go? So we try to answer that question that it will work or not. And another question is when we are measuring this system, we are calibrating system in a static load, but we are measuring dynamic to measure the rail tie interface reaction force. So how this performance is going on there. So first we numerically study how it can affect. So I create a full scale model and track the different shear strain along the neutral axis of the rail. So in here it shows that the rail is actually supported by 2 cross tie, but I changed the cross tie support condition variation and want to track how it is impacting the shear strain that we are measuring along the neutral axis of the rail. And I observed that even if due to the change of cross tie support condition, the shear strain pattern along the neutral axis changes, but their difference is always keeps constant, which is the 516 microstrain, and that is related to the applied load through the geometric property of the rail. In another case, in same numerical model I use and apply different A-frame dimension. And I observe that as long as we are measuring the shear strain at point A and point B, we are okay. But outside that region, there is a variation in shear strain. So if we are in between these two ties, we are okay. So now these two concepts we also test in the field, how it is it actually working or not. So we do some instrumentation in the field, and we install a creep circuit for the measurement of the wheel load, and we install 2 tie circuit so that we can measure the rail tie interface reaction force. And to validate that measure rail tie interface reaction force, we installed a conventional load cell and instrumented tie plate so that we can cross-check how the strain gauge is performing. So as shown in the pictures, the top picture showing the load cell that is installed on the rail tie interface, and it was in the second row showing the instrumented tie plate, which is also a strain gauge based measurement system. But it is installed in between rail and tie interface. And a last bottom row showing that the installed strain gauges. So the first we check that how our 3-frame condition that we mentioned before is performing. So we apply certain amount of load, which is 111 kilonewton load, and we track the strain output, which is differential shear strain in terms of voltage. So we find that in all 3 cases, no matter which configuration we are using, the voltage variation is almost constant, means similar. So we came to the conclusion that no matter what types of A-frame we are using, is giving us the same output. So the calibration process is kind of free from, it does not impact what type of A-frame we are using, or the last one, which is I call car body. So this is one of the conclusion we got. Then we shift that A-frame configuration on top of the tie. So we installed in two locations, we install the tie circuit to measure the rail tie interface reaction force. So we apply load on tie 1 and tie 2, and we find that the strain gauge is actually measuring the 96% of the applied load for tie 1, sorry, 89%, and for tie 2, 96%. And when we observe the same times, the load cell and instrumented tie plate, load cell is installed underneath the tie 1 and instrumented tie plate installed underneath tie 2. It is the exact amount that was missing actually transferred through the rail tie interface. So it's those two systems kind of depend on each other. So we want to transfer some more load to check how it is behaving. So we use the rail car so that we can push more rail and see how it is behaving under a static performance. So we applied for tie one, we applied 130 kilonewton load, and we find that exactly the load cell and instrumented type, sorry, the tie circuit one actually measuring 41% of the applied load. On the other hand, the exactly load cell, which is the conventional way of measuring the rail tie interface reaction force, is measuring 37%. So 4% difference. But for tie two, we find they are both match exactly similar. This is 55%. Then we want to check this system underneath the direct dynamic load. So we choose two rail car, and we apply. We run the rail cars over the locomotives over the instrumented section. So we tested 12 times for each configuration. I mean that we ran over the system 12 times. But we also study another thing, that if the track configuration changes, how it is behaving. So here it is showing the only one run where I collected. Here it is showing all the sensor recorded time history data. Now, if we focus only underneath the wheel one, and we calculate how it is measuring the rail tie interface reaction force for case of a strain gauge circuit and load cell. So we see that the applied wheel load is measured by the KIPS circuit is 24 KIPS, whereas the rail tie interface reaction force, the tie circuit one means the strain gauge circuit is measured that as a reaction force is 10.49 KIPS, and the conventional way of measuring that same amount is 9.25 KIPS, which is very close. And for the location tie 2, we see that tie circuit 2, strain gauge circuit 2 is measuring 13.9 KIPS loads, but the instrumented tie plate is measuring 15.91 KIPS loads. So approximately 2 KIPS load difference. So so we can say from this that they are very close to each other. So we want to test this for all other runs. So we did some box plot for that. And here it is showing the 3 configuration we studied. In configuration 2, the tie A is removed. For configuration 3, tie A and tie B both are removed. And we are comparing that a strain gauge circuit and the load cell for location 1. And we see in the plot that for all 12 runs, that means each of the box plots showing 48 data points, and it shows that they are kind of very match each other for all track configurations. But when we test the same system on same way on location on tie 2, we find that only the configuration 1 case, it does not match that much. And there is a difference certain, but for tie configuration 2 and 3, it match very well. So we from that we conclude that the strain gauge circuit that we are using to measure the rail tie interface reaction force can be used to measure the rail tie interface reaction force reliably, and as an alternative of load cell and instrumented tie plate. And other conclusion is that the calibration frame that we are using, or fixture that we are using, we can actually use any of those configuration to calibrate the install strain gauge circuits. And I would like to acknowledge Dr. Harold Harrison and Instrumented Service Inc. and later Kenny hired a staff member to help us and guide us and suggest us to accomplish this project. Here are the couple of pictures in the field, and thank you so much, everyone. And if you have any question, I would like to answer.
Thank you. All right, questions?
Sorry if I missed it. I know you took ties out on the extremities whenever you were doing your test. You took out ties A and B.
Yes.
And I also know you ran your test looking at how one tie was, like in your simulation, was softer, supported with softer material.
Yes.
Did you happen to study one where they actually forced a gap that closed? So the gap closed maybe at 10 tips of applied load. Did you happen to study that case?
No, in the field we did not that.
I think he's asking about in the model. The model, did you study a gap?
No, we did not. But yeah, we put some soft, as a representative of gap, but we did not see any impact.
Questions?